with the session of papermaking. The chairman will be Mr. Amadeu Santos from Valmet, and he will start the working right now.
Thank you. Good morning, everybody. Thank you, Mr. Dils, and thank you, Tecnicelpa, once again for this honor of being here to be chairman of this session. Today, and going to the session, we will have here a clear demonstration about how the innovation and the new technologies can really influence the papermaking. And as a first starting, we will have Markus Jääskeläinen, please.
Yes.
So a small introduction about Markus.
Yep.
So Markus is a Chief Business Officer and co-founder of Analytics. Analytics is the company behind cutting-edge software solutions for more efficient process industry production called Factory Harmonizer. Analytics was founded in 2013 and acquired by Kemira in 2023. Prior to Analytics, Markus Jääskeläinen worked as research scientist in Lappeenranta University of Technology. So please, Markus, go ahead.
Thank you, Amadeu. Can you guys, by the way, hear me right to the back? So good, good. I will not need a microphone then. Yeah, nice to be here. Good to meet you all. I know it's probably not a coincidence that there's quite a few Finnish people here this week because the weather just turned quite bad over in Finland. But let's hope that the topics are also worthwhile us visiting here. So I will be talking today about harmony modeling, which in essence is a technology that is used to monitor and highlight deviations from process production or production processes, and then also prioritize those deviations for higher production efficiency, which is ultimately the goal that all these digital services or services in general are, of course, all about. So I will give you a few principles of what the harmony modeling, so the technology actually is. Harmony modeling is, like Amadeu already mentioned, the technology behind Factory Harmonizer, which is a service that we are providing for various process industry verticals. And then for pulp and paper specifically, we have a service called ChemConnect Harmonizer in Kemira's portfolio. As you already heard, we are now part of Kemira family. So the technology is the same behind both of those services. I will give you a couple of simple examples how those deviations are shown to the users, and then the overall value that we've been able to generate for customers that have been utilizing the service for longer periods of time already. And then in the end, as we are talking about fully automated way of creating models, so automated meaning no domain expertise from papermaking expert is needed for the actual model creation. So that is a very scalable way to generate models for also other purposes than just the monitoring the papermaking process. So I will discuss briefly what those opportunities that we are also seeing and developing at the moment are. And then I guess in the end we will have a short Q&A to summarize. So about harmony modeling, as I already mentioned, we utilize historical data to create models. In fact, that is typically hundreds or even thousands of models of the process in focus. And we only utilize the historical data, not use any human invention, which is a very scalable way, first of all, to build the models and then also to maintain the models so that you would have up-to-date models monitoring your process all the time. So each and every minute is new insights and deviations or the current status of the process being generated by the analytics engine. And then there is the ability also to prioritize those findings so that the people who are responsible for running the process will know where to focus and take the corrective actions. So here in the, Here the bird's nest or the modern art graphic here is actually a copy paper process. And each of these balls represents a tag, so a measurement, be they temperature, pressure, or tension, or whatever it might be. The larger the ball, the more impact it has on other places in the process. And those lines between the dots or the balls are those direct connections between different process measurements. So essentially, harmony modeling is about understanding how different things interrelate with each other in the process. And then that provides us the ability to highlight and identify various types of deviations, also the types of issues that did not even exist in your historical data. So if you think about your pattern recognition approach, where you basically take your historical data and try to find out chains of events that lead to unwanted things, such as runnability issues or quality defects. We are able to identify issues that didn't even exist in the historical data with this approach, as the first layer is to create this kind of a network, how different things relate to each other, and then we create the harmony values for each of these measurements. So that would mean that if this, for example, the blue dot here is a temperature measurement, we would not consider the actual true measured value from the physical instrument at all, but instead we detect from all the other measurements around where the measurement, so the temperature, for example, would make sense to be at. That would be the harmony value. And then as we bring in the actual measured value, if those two are hand in hand, there we are in so-called in harmony. If there is a difference between those, that is a harmony deviation. And then the next layer of the machine learning is to understand which deviations are more critical than others, right? So not all deviations in your papermaking process are created equal. So if you think about soft sensors, for example, you need to generate a measurement or a value from something that is not physically or is not measured with a physical instrument in real time. So ultimately what we do basically is that we create hundreds and hundreds of those kind of like soft sensors for those measurements that are already measured with physical instruments, and then prioritize if there are any deviations there. So that is, we take into consideration the whole process. So if you're talking about paper and board making process, that would be from head box to reel, and then also augmenting those models with batch preparation and water circulation, so like these sub processes. So the entire process is in focus here. We've actually written another paper earlier where we compare different types of ways to build models for papermaking process, where we basically compared the strengths and weaknesses of different approaches, from spreadsheet simulation to harmony modeling and everything in between, with this modeling triangle approach, just to highlight the strengths and also the shortcomings of each technology. So the ease of use is perhaps the most important aspect of this type of technology. So you don't need to have data scientists or statistical skills in order to build the models, and you simply as an operator or engineer start paying attention on the inside. So it is very easy to set up and start using, and also to keep up to date. We can take pretty much all the data from the papermaking process. We do not need to handpick what are the critical ones, so it's easy to generalize for various types of processes. And then the accuracy is better than, for example, if you would have your thresholds or operational windows for for your in your DCS system. So you could also consider this as a dynamic operational window. So given the current status of your process, where each measurement would make sense to be at, this is what we are basically creating here. So a couple of simple cases, what or how we basically introduce the information for the users. So for example, in this case, the technology identified that the logics, how the heat recovery system was operating, were pretty inefficient, and by highlighting which of the set points were perhaps a bit too high and some of them a bit too low, our customer was able to immediately revise and recalibrate the logic how their heat recovery systems worked, and they calculated themselves that only this single finding was worth more than 200,000 euros a year in better energy efficiency. Or in some other case, here the black line is the actual measured value, and then the blue line is the harmony value, so where it would make sense to be at. So for example, a emerging clock we are able to identify much earlier than your fixed threshold alarm system. So already when the pressure of the machine that is putting, for example, here in the sizing spring pump is working more and more and more, but everything else stays more or less the same. So that's why the harmony value would assume that this also should stay on a similar level. This was a clear indication that there seems to be an emerging clock. So before this actually became a problem, they were able to make corrective actions and also to have a battle plan for similar types of situations. These are just two very simple cases that I'm presenting here. There are also more, I'd say, complex related to how chemistry of your process has an impact on your or is related to the machine performance in the papermaking process, for example in retention control or steam consumption. So those are often a bit more complicated, but also the types of findings that we are able to highlight with this technology. So all in all, of course, it's about how can we be beneficial for, or how the technology can be beneficial for those that are actually responsible for running the process. So the OEE, the overall KPI of every paper machine, when comparing the time before this technology and after, we've been able to generate 1 to 2% improvement in OEE, which obviously is a significant monetary improvement. We do that by, let's say that on average, in normal conditions, we would probably generate 3 to 5 findings per day. Of course, it depends on the status of the process, whether there are more or less of those critical findings. And the idea is that when over time you are able to get rid of also those minor deviations, your process is more stable. When you are in more control of your process, you are able to push your process towards your efficiency targets, whether it's higher speeds, more efficient raw material usage, or even introducing cheaper raw materials into your process. So I already alluded to some soft sensors. So besides from monitoring the entire process, we also utilize the technology in building soft sensors. So basically creating a real-time measurement for some parameters or variables in your process that are traditionally, for example, coming through lab testing. So for example, you take a sample once a day, send it out to the lab, and then the next day the results come in. For example, in mechanical pulp production, we've generated a soft sensor for bulk measurement, which came previously in once per day. So what now is possible is that the the mill has the estimation or the computed value of bulk available each and every minute, so the current status of the bulk, and we tested the accuracy against the lab measurements, which was the error was on average 2.2%. So depending on, we are also developing those soft sensors for sizing and strength and other quality KPIs as well. So depending on the starting point, we can anyways quantify how accurate the soft sensor is with this type of technology, and that is then the easy way to decide whether that is useful or not. And then also, of course, how chemical performance, as we are providing the service with, as Kemira family, how the chemical performance is impacting the overall production performance, how the interrelations between machine performance and the chemistry, the transparency to those issues and phenomena are much more improved with this type of technology. So from retention to many other, let's say, more sophisticated ways to measure the chemicals performance in the process, we are able to relate that performance into the overall process behavior lot more accurately. And then also, when you are starting up a new process, you might be running some trials. Even though you are far from your optimal status, this type of technology is able to highlight how changes, or for example increasing the speed, has impact other parts in your process, and that way speed up the process of starting up and getting up to speed with your production. That was a brief introduction, so hopefully you will have some questions after these colleagues' presentations here. Thank you very much.
Thank you, Markus, for the insights. I'm sure that there's a lot of questions. So the next session will be Tuuli Silomaa. Please go ahead. Tuuli is a young talent, earned her Master of Science degree from University of Oulu, New Zealand, in mechanical engineering in 2017. During her studies, Ms. Silomaa worked as a process operator at Stora Enso shipping factory in Oulu. After her studies, Ms. Silomaa worked for Valmet as a development engineer in several demanding product development projects in roles R&D for 4 years. Since 2021, she has worked in wet-end R&D as a product responsible development engineer for the sleeve roll technology. So, please, Tuuli, the floor is yours.
Okay. Hello everyone, my name is Tuuli Silomaa and I will tell you how Valmet's novel sleeve roll technology transforms forming section. The idea of the sleeve roll technology is very simple. Web is compressed between two forming fabrics against a small radius shoe. Depending on values of the forming fabric tension and the small radius shoe, it's possible to create very high dewatering pressure levels, up to 150 kilopascals. In the basic circle of the sleeve roll, dewatering pressure created by wire tension is moderate. But when web's going over the small radius shoe, dewatering pressure increases steadily towards the maximum compressing pressure. And this steadily increasing compressing pressure doesn't cause any defects to the web. Dewatering pressure in traditional dewatering elements is around 50 to 40 kilopascals. And with good roll or high vacuum boxes, it is around 60 to 70 kilopascals. So, compressing with sleeve roll technology is a significantly more efficient way to remove water from the web and create high vacuum. So, while pressing only on press section, in the left hand we will see the traditional way to remove water from the web by pressing, by suction, which is preferred from forming section. And it takes a lot of energy to produce high negative pressure. The same thing is handled by pressing on press section familiar way. Why not use pressing on forming section as well? Pressing is significantly more efficient and the results are same or even better. Sleeve roll technology has born from this realization. Depending on forming section concepts, incoming consistency to the sleeve roll is very low, 4 to 6%, and the outgoing consistency from the sleeve roll is constantly high, 12 to 14%. Sleeve roll technology doesn't need to use vacuum or high pulsation to remove water from the web. Water comes out from the web with increasingly high compressing pressure and centrifugal forces. And the water jet is collected to the save oil pan after the sleeve roll. Sleeve roll structure consists static beam, small radius dewatering element called shoe, gliding shear face before the shoe, rotating heads, oil evacuation, feeding and evacuation systems, and also a lubricated polyurethane belt rotating around the roll. Valmet has tested sleeve roll technology in many forming section concepts and positions in pilot trials. Sleeve roll shoe can be in almost any compass directions, and that's why this new technology is applicable for both new board lines and rebuilds. Sleeve roll technology is already established technology in hybrid formers and the board cat formers. And I will tell you those results later. Sleeve roll technology can be also used to combine layers together. Densified web improves ply bond strength and can reduce the need to use wet end start. There is a couple of possibilities to use sleeve roll in combining position. At the multi-foot linear end of the forming table, sleeve roll technology increases production capacity of the top former without extending foot linear table. In the cup former with shoe and blade technology, here, sleeve roll is placed on control position. Sleeve roll technology doesn't need vacuums, so power consumption of the vacuums is significantly reduced in forming section when there is no need for control. And in cap former with shoe and blade technology is possible to increase production capacity and end quality of the product with sleeve roll technology. Valmet has delivered 2 production scale machines running with sleeve roll technology. The first former with sleeve roll technology started up in 2021 in Ain Pulp and Paper's PM3 in South Korea. This hybrid former rebuild produces recycled fluting grades. And target of this rebuild was to increase production capacity and end quality of the product. In this rebuild, top fabric loop here, forming roll and the sleeve roll was added to the conventional foot linear. Trials results from IMPM3 are equal with pilot trials. Sleeve-roll removes water very effectively from the web. And that's why IMPM3 doesn't use almost any vacuums before the sleeve roll. Ingoing consistency to the sleeve roll is low, 6%, and sleeve roll technology increases dry solid content to the 13%. And dryness end of the forming section is very high level, 25 to 26% with sleeve roll technology. Sleeve roll technology has potential to increase production capacity of forming section. On IMPM3, production capacity has increased by up to 18%, of course, depending on basis weight. After sleeve roll installation, production capacity has been up to highly over 9 tons per hour per meter, which is nearby production level of new modern machine. Results from IMPM3 shows that the biggest improvement in quality properties is in formation. Sleeve roll technology removes water very effectively from the web, and it is robust for ingoing consistencies. So that enables to use higher headbox flow rate. And better formation usually means better and equally quality properties of the web. In the forming section, web's quality properties can be modified to the consistency of 6 to 8%. There is also possibility to change filler and fine distribution in that direction. After consistency of 8, the main principle of the forming section is just increase dry solid content of the web. Results from IMPM3 shows that the biggest quality improvement after formation is in bonding strength. Compressing dewatering makes web more uniformly dense, and that has positive effect to the bond between fibers when fibers are closer to each other. IMPM3 has able to also increase MD strength to get better runnability without almost any loss in CD strength. With sleeve roll technology, it's also possible to achieve stable dryness profile in MD-CD direction. And these two has positive effect to the runnability and the time efficiency for the board machine. And IN has seen less breaks and quick changes of basis weight after sleeve roll installation. The second sleeve roll former started up also in 2021 in Papermaking PM5 in Germany. This new board cap former is the world's widest high capacity containerboard line producing recycled, fluting and liner grades. Quality and dryness results from Papermaking PM5 are equal with pilot trials and also pretty equal with IMPM3. Sleeve roll technology reduces need for vacuum on forming section. Papermaking PM5 has been reduced dry power consumption by 10% when there is no vacuums before the sleeve roll. When there is less vacuums, there is also less friction between forming fabrics and dewatering elements. That's why dry power consumption is reduced. With sliver technology, dewatering in palm PM5 in sliver position has been up to 50 liters per second per meter. Of course, depending on forming section speed and incoming consistency to the sliver. And if we compare this to the traditional podcast former, the plain roll in this sliver position doesn't remove almost any water from the web. Trials results of the forming section has been also very good level, up to 24%, and there is no cultural end of the forming section. And we have seen the more water you remove with sliver technology, the more outgoing dryness you will get end of the forming section. In summary, sliver technology removes water very effectively from the web. With sliver technology, it's possible to reduce power consumption, energy consumption, because water comes out from the web with compressing, with forming fabric tension and small radius tube. And due to low incoming consistencies, it's possible to increase production capacity.
Thank you, Tuuli. Our last presentation of this session, it's Mr. Biermann. So Christian, born in 1965, studied chemistry at University of Munster. Following his doctorate in 1994 at the Institute of Organic Chemistry, he spent a 1 year of research period at the University of California in Santa Barbara. He began his professional career as a laboratory manager at Oscar Novel Chemicals in Durham. There he was involved in the development of new surface sizing and wet strength agents before moving to paper chemical sales in 2003. Since 2020, Mr. Biermann has been working as manager of wet end and surface solutions in the application and marketing group at Chemira. His main focus is on retention, sizing, and surface treatment process, and the introduction of new applications. So please, Christian, the floor is yours.
Yeah, thank you very much, and good morning, everybody, and welcome to our presentation on deposit control. And the title is a little bit bulky, but it describes what I want to talk about. So I will first give you some background information on deposit control. Then I will introduce you to a new chemical, which we think is very well suited for the control of deposits in the paper machine circuit. Then I will discuss or show you some of possibilities how to measure the contamination of a paper machine circuit in laboratory and also online. And last but not least, I want to discuss with you the possibility, if it is possible to build a control loop to control the dosage of the fixative or the amount of deposits in the paper machine circuit. And okay, let's go to the background. So deposits are a major source of problems. They cause runnability issues and quality issues, which may cause that some paper which is produced needs to be rejected. The hydrophobic particles in the systems are the major reason for these deposits. And to cope with these deposits, of course, it's very important to have a very efficient stock preparation system, because things which are not removed when you prepare the furnish, it's very difficult to get rid of it later on at the paper machine. Then you need to find a suited fixative. There are a lot of chemicals available as a fixative, but you need to identify the one which works best for your situation. And then if you want to control something, you need to be able to measure it. The measurement can be done in laboratory, which is okay, but ideally you would have to have an online measurement. And then last but not least, the question is, can you make an automatic control loop, or will you just have a reading and the operator adjusts the dosage, for instance, accordingly? So this ends up in this triangle. So runnability, quality, that is what we want to achieve. You need the suited fixative. ideally you have an online measurement, because on that one you can then base the control. Okay, the product which we developed is called Phenopol ER9920E, and we call it a quick inversion polymer. The reason why we call it is because it's an emulsion polyacrylamide, but it is very easy to make down, so you don't need any traditional make down equipment. What we need is more or less a pump, so we can dose from IBC or from tank. Then we need a pump, the dilution or inverting water, and a static mixer, and from there it can go directly to the paper machine. So no curing or maturing tank is needed. It's very simple actually. It's very straightforward. The polymer as such is a high charged polymer. It has the food compliances which are needed, and also like Nordic Swan, if that is of interest, or Ecolabel. And molecular weight, like, it is somewhere between the traditional polyacrylamides and the traditional fixatives which are used, so somewhere in between. And here's a case study to illustrate the performance of it. So this is a newsprint machine. It's a big one, running at 1,800 meters per minute. And the customer has problems with sticky, which accumulate in the drying section and then causes holes and breaks. So quality problems and also runnability problems, as I introduced. And what we did is we started to use the Phenopol ER9920E. Without a maturing tank, as I said, just inline dilution, we started to dose it to the outlet of the machine chest before the machine chest pump, because then we get a very well mixing in at this point. And with this treatment, the stickies have been eliminated. On top of it, it was possible to reduce the traditional fixative, which was used before, and also we are having savings in the need for retention polymer. What is interesting is the ash level in the sheet increased slightly, even though the white water consistency is controlled at this machine, and the white water consistency stayed the same. So that means, there's the incoming recycled fibers are more efficiently used, and there's also less dry waste, of course, which leaves the paper machine. So this is running really well. Okay, so the system is running really well. And the question is, can we measure it? In laboratory, we can measure it very well. Therefore, we use the system flow cytometer, or in Chimera, the trade name is Flyto. And the Flyto is a standard lab method. You can measure the total number of particles. You can distinguish between colloids, small, and agglomerates. You can count the number of these particles in these size region. And you can stain the particles, and with this you can distinguish between hydrophobic particles and non-hydrophobic particles. What is the limitation is 30 micrometer is the biggest particle size you can measure. And here the colleagues measured all hydrophobic particles, so the size of the column, it's very small, unfortunately, the font size, but the size of the column just indicates how many hydrophobic particles were seen in total. And once we started the trial, within 4 days, the number of hydrophobic particles decreased significantly. Except towards the end of this period, suddenly the numbers went up again. And as it was seen, we had issues with the flow meter, so in reality we were not dosing the fixative anymore. And once the fixative was dosed, the situation immediately turned again to the normal low levels. So in laboratory it's very well possible to measure the situation in the paper machine. So we see the buildup of hydrophobic particles, and that results in the problems which we observe in the drying section. And the next step at this customer will be to introduce the system called Fly-to-Light. The Fly-to-Light is a patented instrument from Chimera, which is able to do online measurement, very similar to the measurements of the Fly-to in laboratory, but in the paper machine circuit. And it gives the same information, so total particle counts, counts of colloids, fines, and agglomerates. But the main difference, or interesting difference, is the particle range which can be measured is much higher. We also start in micrometers, but we are able to measure also in millimeter range, which can be an advantage because, let's say, a deposit of 10 micrometers will not cause a break in the drying section, but it may build up later on, so that is the problem. Again, we can see the total hydrophobicity, and also we can distinguish between the hydrophobicity of the colloid fines and agglomerates fraction. So this is a little bit represented here. Okay, the instrument is a standalone instrument as such, so everything is just connected to it. It's automatically flushing, and it's very robust. And here's just to illustrate a little bit. So here we saw once the amount of hydrophobicity of the fines. If this hydrophobicity increased too much, they had breaks from holes in the drying section. And so they introduced warning limits. And they saw once they went above these warning limits, they had an increased amount of breaks. And what they do now is they use these warning limits and the measurements to take countermeasurements. Like, for instance, increase the fixative, or another alternative is sometimes just to dump the white water tower and to clean it. Yeah, so summary so far. So we have a very efficient fixative. We can measure the effects of the fixative in the CIS paper machine circuit. And now the question is, deposits or building up of hydrophobic material or also coming down is a long process. So it's not a quick control loop, it's a very long control loop. And how can you control this control loop, which is really a challenge. And therefore the system ChemConnect Agile was developed, and we call it a smart control circuit for additive dosing. Smart because the dosing is based on multiple parameters or measurements from the paper machine and or online measurements which can be provided by Chemira. And agile because it's very easy to change the control loop logic of the controller. So it's not a lot of hardware work needed or a lot of programming needed. So somebody who is skilled in the chemicals can easily change the control logic. And to explain the vocabulary a little bit, so the dosing control logic consists of certain dosing rules. It can be stock flow, for instance, when it reaches a certain number, we dose more or less, level of a tank, for instance, and so on. And if you want to change, for instance, the oxidative redox potential, when it goes above 300, I want to dose more, or I want to dose less, meaning that the pump is off for, instead of 360 minutes, it's off for 400 minutes. That is very easy. You can do with any controller easily. But if you want to introduce a new dosing rule, in this case, start dosing when the oxidative redox potential drops below a certain level, that is very complicated in a normal historical or standard controller. And there, this ChemConnect Agile dosing has its strength. So it's very easy to change and implement the change to the controller, and it works very well. What is nice, we can collect a lot of data from the paper machine and our measuring devices, and also we can do calculated signals. So sometimes you may be more interested in the slope how a value develops than in the exact value itself. And so we could make just calculate the slope and use this as a control dosing rule. And in reality, it looks like this. The ChemConnect unit, it's getting raw signals. It's unlimited in run, and you can do a lot of calculated raw signals from this. Everything is local, so the controller is local at the paper machine, and then it locally communicates with the pumps and with the mill online data and the data from the Chemira unit. Only when we change the rules, those come from a cloud, so come from the outside via remote connection. And the rules are changed from, we say, expert user. It's very often an application specialist from Chemira, and of course you will consult with the paper maker as such with the paper production. And the nice thing about the software is he can test the rules on historical data. So he can implement a rule and see what will happen to the dosing based on based on historical data, does it still make sense, or will he get what he wanted to achieve? Because sometimes you introduce a new dosing rule and suddenly there's no dosing at all anymore because you made a mistake. And that way, it's a very safe way to change something because you can simulate the new dosing rules on the past. It's always, due to this, it's always up to date. And then the unit can directly control the dosing pump, or it can go via the DCS, and the operator decides if he wants to have this change of dosing or if he doesn't want to have this change of dosing. Of course, it needs to be interlocked with the paper machine. It needs to be interlocked with the paper machine. For instance, if we have a biocide, we don't want to dose the biocide when the paper machine is not running, for instance. Okay, here's a very small example, and it's a folding boxboard machine, it's quite big, and it was for microbiological treatment, more or less they were able to lower the biocide consumption for catalase control, and outcome was they produced 5,000 tons in a 7-month period, more than they would have normally done when compared to the historical thing. So to summarize it, we have this triangle, and we can fill this triangle with the Phenopol ER9920E as a very well working fixative, which really shows outstanding performances. We can measure, we can introduce an online measurement which is checking the situation in the paper machine, and with this online measurement, we think that we are able to control this very long control or very slow control loop very well. Thank you very much for your attention.
Thank you, Christian. So now it's time to open to the audience. There's 3 very good applications for our papermaking, and I would like to know who is ready enough to start with some questions to our dear guests. Yes, please.
This is a question for Markus. How does the model building process improve these standard, center lining pieces? So, how does that help you identify and better track what might be the root cause changes compared to something of just looking at center lines and plastic?
Basically, what we do is that as we relate the logical levels of each measurement minute by minute, so basically what we would have is like a dynamic center line in a way. And also, as we build those harmony models, you saw the network. So the user can also see not just the deviation from that thing that was highlighted on top of the priority list, but also can drill down into the models, basically to see which were those measurements that were primarily used to compute the harmony value for my target value, and how are they behaving. So am I looking at the root cause here, or is this an indication of something that is happening elsewhere? Is this just an issue in one single position in my machine, or am I seeing similar or let's say parallel behavior in a way in multiple places? So I know that this is a larger phenomenon than just a single measurement. Hopefully that answers the question. Thank you.
Thank you. Any other questions from the audience? Yes, please, go ahead.
From your experience with the slave form evolve, what is the impact on both, especially in the fine paper grades?
Zero technology makes wet uniformly dense, so it has mild effect to the bulk. So we haven't researched it very deeply, but it has some effects to the bulk.
Thank you. Some other questions from the audience? We still have 10 minutes, so please go ahead.
Yeah.
For your most special gathering data, how long does more or less, on average, a model to be a robust model takes?
So do you mean that how much historical data would we need? Yeah, good question. We typically start with 12 months of historical data. Then depending on the nature of the process, so how many, for example, grades we are producing, how much variance there is in the process, each and every model update would utilize typically data from 3 to 9 months. Would be, I guess, the rule of thumb. But we will find out that as we create the first models, and then as we put the live service up and running, then we will know what makes sense based on the characteristics of the process.
Thank you. Please go ahead.
Also, a question for Markus.
Yep.
So we know that the quality of the data for building the modeling is mandatory. So I would like to hear from you, what are the challenges that you face on this? When you have got the best quality, what are the tasks that you need to follow to guarantee that you have reliable data? And the second one will be about the soft sensors. From the sensors that you already implemented, what would be a benchmark correlation from the variable, from the real variable?
Yeah, so the first question about, sorry, can you phrase the first question? What was the
quality of the data? What are
quality of the data? Yes, of course. Yeah. So what we always do is a, or we call it a data health check. So before we deploy the first models, we have that is not a fully automated, but I would say semi-automated pipeline that we run through the historical data, which basically identifies the continuity, perhaps some outliers in the data. So not just for harmony modeling purposes, but I'd say machine learning purposes in general, how good the data is. And if some of the tags do not even pass the threshold, so we would not even include those into the modeling at all. So that is what we do always. And then we have monitoring in place for the data stream so that we identify, let's say, drastic changes or mishaps in the data stream in live use. You are correct that crap in means crap out basically when it comes to data. So that is the most important thing, and we do pay a lot of attention to that. But I would say that the combination of data health check and then thoroughly curating the first model iterations typically reveal us if some data is not useful or how accurate those models are. And then the second question was related on soft sensors.
Yes, correct.
So were you interested about the accuracy of those, or what was the question?
Accuracy, for example, of course that you, if you bring a soft sensor for a dedicated variable,
Yeah.
you should compare how close, how far you are.
Exactly.
So I'm interested to say on our benchmark,
Yeah.
it would be 90%, 80%, 100%.
Yeah, it depends on the target variable. We aim for at least or maximum of 5% error when comparing two lab measurements. For example, bulk measurement in PCTMP production, we were able to generate an accuracy of 2.2%. So basically the average deviation when comparing to lab measurement was 2.2%. But I guess the strength of this type of technology is that you not only get to develop the soft sensor in a scalable way, but you can immediately quantify the accuracy and then leave it out to the customer or the end user to decide what is the required accuracy level. And we can provide that accuracy information, continuously as also those lab measurements come in. So it is I'd say a pretty good way to validate the usability.
Good. Thanks for the presentation. Thank you.
Thank you, Markus. Any other question from the audience? Please go ahead.
I'll ask one for Chris. So you talked about soft sensors now. You mentioned this online sensor or measurement that you're using. Is there opportunity to utilize soft sensors to better improve your control loop, or does your sensor provide all the feedback that you need?
I mean, in reality, every sensor can be used, so it's not limited to physical sensors or measurements. It can also be a soft sensor, of course. And I mean, the question which you are asking is also interesting. I mean, we have the ChemConnect Agile, and the question is, for instance, if like the harmonizer could also do the same job instead of the ChemConnect Agile, there's also an opportunity. And also the harmonizer could use the information from the ChemConnect Agile. So I think everything goes hand in hand there. But also I think it's an interesting question when you start a new fixative at a paper machine. Turn around and you don't have to, when you start a new fixative in the paper machine, then of course you change the model in a way as well. So I think then the harmonizer model is able to learn, so you need a self-learning model as well, because I introduce a completely new chemical to the system, and then of course changes the wet end conditions a lot. So everything can go hand in hand. Then of course it's a matter of where you start and how complex you accept the system to become. Thank you.
Thank you, and thank you for the good questions. I think today, as with all the challenges that we have on the paper making, to have this kind of innovation, using a lot of technology, digitalization, to improve our efficient, to move to a more sustainable process. I think that's why we are here, and then those are the kind of solutions that we are really looking for. So a big applause to our directors. Thank you.